Take the three lightest elements forged in the first minutes after the Big Bang. Hydrogen, helium, deuterium. The theory nails all of them. Then there's lithium, and the universe made only a third as much as it should have. In the first few minutes, the entire universe was a nuclear furnace. Protons and neutrons fused into the lightest nuclei, then everything cooled and the reactions shut off. That 20-minute window set the chemistry of everything that followed. Big Bang nucleosynthesis is one of the most tested predictions in all of cosmology. Feed it a single number, how many baryons, how much ordinary matter the universe holds, and it tells you exactly how much of each light element you should find. For deuterium, that prediction is spectacular. Measurements from distant quasar light passing through primordial gas match the theory to within a few percent. Helium-4 agrees too. The map fits everywhere except one corner. That corner is lithium-7. Theory says the young universe should hold about 5 lithium atoms for every 10 billion hydrogen atoms. The oldest stars show closer to 1.5, a factor of 3, simply missing. To measure primordial lithium, you look at the oldest, most pristine stars in the galaxy's halo. Stars almost untouched by later generations of stellar pollution. In 1982, Francois and Monique Spite did exactly that and found something strange. Across a wide range of these ancient stars, different masses, different temperatures, the lithium level was nearly identical, not scattered, a flat line, now called the Spite Plateau. That flatness was taken as a fingerprint of the Big Bang itself. If stars had cooked up their own lithium or destroyed it at random, you'd expect a mess. Instead, one clean, universal value, a relic from the beginning. For years, though, nobody knew the universe's exact baryon density, so the plateau's mismatch was hard to pin down. Then the cosmic microwave background changed everything. NASA's WMAP satellite, and later Europe's Planck mission, measured the faint afterglow of the Big Bang with brutal precision. From it, they read off the density of ordinary matter directly. No stars required. When that number went into the nucleosynthesis equations, deuterium and helium fell perfectly into place. And lithium was predicted 3 times higher than the plateau actually shows. 2 completely independent methods, 1 stubborn gap. The missing lithium leaves 3 suspects. Either our measurements are wrong, our nuclear physics is wrong, or our physics of the early universe is wrong. Each has been chased hard for decades. Start with the stars themselves. A star's measured lithium depends sensitively on its surface temperature, which is notoriously hard to nail down. Get the temperature scale slightly wrong, and the whole plateau shifts up or down. But careful recalibrations haven't come close to closing a factor of 3. And better data made it worse, not better. The plateau held firm across independent surveys. The measurement isn't the culprit. The second idea is subtler. What if the lithium really was there, and the stars themselves quietly destroyed it? Lithium is fragile. It burns at just 2.5 million degrees, far cooler than a star's core. If gas circulates from the surface down into those hotter layers, the lithium gets consumed. Over 10 billion years, a star could slowly erase its original supply, dragging the plateau down from 5 to 1.5. There's a catch. Different stars mix differently. If destruction did the work, the plateau should be scattered and messy. Instead, it's flat. Any mechanism that removes lithium has to remove exactly the same fraction from wildly different stars. That's an uncomfortable coincidence. It's like finding 100 different ovens that each burned away precisely 2/3 of their bread. Possible, but it demands a There is a serious version of this argument. In 2006, a team led by Andreas Korn studied stars in the globular cluster NGC 6397. They modeled atomic diffusion, lithium slowly sinking under gravity. Balanced by a gentle turbulent mixing, their models could reproduce a flat plateau and recover much of the missing lithium. It's the strongest stellar solution on the table. But the turbulence has to be tuned by hand, and not everyone is convinced it works for every star. Suspect 3. The nuclear reactions themselves. Most primordial lithium-7 isn't made directly. It forms as beryllium-7, which later captures an electron and decays into lithium. Change how beryllium-7 is created or destroyed, and you change the whole answer. Maybe an overlooked reaction quietly wiped out beryllium-7 in the early universe. A resonance that laboratory experiments had simply missed. If such a reaction existed, the lithium prediction could drop right into line. So physicists went hunting. At the lunar experiment, buried under the Gran Sasso mountain in Italy, they remeasured the key beryllium-7 reaction rates directly, shielded from the interference of cosmic rays. The rates came back consistent with the standard values. No hidden resonance large enough to matter. One by one, the nuclear escape routes were measured and closed. That leaves the most radical option. The physics of the first 3 minutes wasn't standard at all. Something exotic was present during nucleosynthesis, tampering with the light elements as they formed. One class of ideas involves hypothetical particles, decaying or annihilating during nucleosynthesis, injecting energy or extra neutrons at just the wrong moment, preferentially wiping out lithium while leaving deuterium and helium mostly intact. The trouble is that precision cuts both ways. The same tinkering that removes lithium tends to disturb deuterium, and deuterium is measured too well to allow much room. New physics has to be surgical to survive. Others have proposed that fundamental constants, the strength of the nuclear forces, were slightly different in the early universe, rebalancing the reactions. But there's no independent evidence that any such constant has ever changed. Then the picture got stranger. As astronomers pushed to the very oldest, most metal-poor stars, the ones closest to primordial, the lithium didn't hold at the plateau. It fell off a cliff. Below a certain metal content, the neat, flat line breaks apart. Some of these ancient stars show far less lithium than even the reduced observed value, and huge scatter, star to star, with no clean pattern. That's the deeper puzzle. The plateau we trusted as a clean relic isn't clean at the extremes. Whatever governs lithium in these stars is doing something we don't understand, which undercuts using them to measure the Big Bang at all. The measuring stick itself may be bent. There was even a second lithium problem. In 2006, Martin Asplund's team reported surprising amounts of lithium-6, a rarer isotope, in old stars, far more than the Big Bang could ever have made. That one has largely dissolved. The signal came from subtle asymmetries in the star's spectral lines, mimicked by convection. Better three-dimensional models made most of the excess lithium-6 vanish. The lithium-7 gap did not. After 4 decades, no single answer has won. The nuclear route is essentially closed. The new physics route survives, but strains against how well we know deuterium. The consensus is drifting toward the stars. Most researchers now suspect the primordial lithium was there all along, and that stellar processes, diffusion, mixing, depletion, quietly hid 2/3 of it from us. But drifting toward is not the same as solved. What keeps this alive is what it threatens. Big Bang nucleosynthesis is a cornerstone, proof we understand the universe seconds after it began. 2 of its 3 predictions are triumphs. The third is a crack running through the foundation, worth more than 100 confirmations. For now, the factor of 3 just sits there. Too small to break cosmology, too stubborn to explain away. Is the lithium hiding inside the stars, or did the early universe never make it at all? The cleanest test may be finding primordial lithium in gas that never passed through a star to burn any away. Until then, one missing element. Two very different stories about the first 3 minutes.